Okay, so we knew at the outset of chapter 5 that this was going to be a labor-intensive process. We just tons of topics, or rather, I should say, tons of terms. And here's another one. We're going to tease this out pretty well, but it's pretty intense. So I hope you have some paper ready to take notes. And let's get started. So enthalpy, we're going to talk about enthalpy a great deal. It turns out it's going to be super useful to us, and we're going to talk about a couple different kinds of enthalpy or uses of it. So enthalpy is well, let's first of all go back and talk about thermochemistry. It's a branch of chemical thermodynamics, and it's the science that deals with the relationship between heat, work, and other forms of energy. So substances act as reservoirs. This is important. Substances act as like reservoirs of energy, meaning that energy can be taken, added to them or taken from them. Energy stored in a substance when the kinetic energy of the atoms or molecules is raised. Okay, haven't really got to the point yet. Okay, so here it comes. Internal energy is all the possible kinds of energy present in a substance, and we oftentimes use E as the symbol for that. Your textbook uses U for the symbol of internal energy. It turns, as I'm doing this, I may slip into E accidentally when I'm doing this because I'm so used to using E. But let's go with the way that your textbook calls internal energy, capital U. Okay, so the internal energy is the relationship. The relationship between change in internal energy, delta U, and heat and work is summarized in the first law of thermodynamics, which goes like this: the change in internal energy is equal to the heat plus the work. Okay, Q plus W. So if the system absorbs heat, then Q is going to be positive, and if the surroundings do work on the system, it's going to be positive. Okay, and of course, right, because the change in U is equal to Q plus W, that would be going up. The internal energy of the system would be going up if heat is being added to the system. So that would be positive, and this makes total sense, right? And if work is being done on the system, then the internal energy would be going up, right? So you would want W to be positive. And of course, the opposite is also true. If the system is releasing heat, then Q is going to be negative. And if the system does work on the surroundings, then W is going to be negative as well. All right, so remember, delta U is equal to Q plus W. Simple enough. So sort of pictorially, we'll say that if the system is transferring heat to the surroundings, then Q is going down. If the surroundings are transferring heat to the system, it's going to be going up. Okay. So work is another thing. I don't think we've even talked about work yet, right? A type of work called expansion work, and this is the bulk of the work we're going to be talking about, is when a system pushes back in the surroundings against the restraining pressure, okay, or the surroundings compress the system. So it's essentially going to be PV. Work is going to be defined as PV, and it's actually going to be negative PV. We'll see in the next slide. So consider an internal combustion engine system where the system is equal to the gasoline plus the oxygen, right? That's the reaction going on inside the engine, okay? Gasoline plus oxygen. The surroundings is the rest of the engine, okay? The reaction is exothermic because you would imagine gasoline lets off energy, right? And that's why we use it to drive our cars. So heat's being given off to the surroundings. Q is going to be negative. The reaction pushes the pistons out, right? P delta V, so volume is getting bigger of the pistons because the pistons are getting pushed out, and so W is going to be negative. All right, and the internal energy of the system is going to decrease, right, because your gasoline and your oxygen are losing energy, and they're losing energy in the form of heat and work, where the work is driving the car down the road. Okay, now this is a state function. Internal energy is a state function. That means that the change in energy doesn't matter how the state is reached. It's just the difference in energy between the beginning and the end. And so the example that's given in your textbook is, suppose you have a mountain climber, right? So the mountain climber starts down here at the base and ends up right here. And it turns out it doesn't matter which path they take. It's the change in energy between the beginning and the end that is what we're calling the internal energy. So, of course, in real life, it does matter what path you take. But in chemical and physical systems, it doesn't matter. what you take, because we're not considering like how much energy you lose from sweat or whatever, right? Okay, so the next term, and this is really the big one, enthalpy, is defined as the sum of the system's internal energy. So enthalpy is defined as the sum of the internal energy, and that's the sum and the mathematical product of the pressure and the volume, right? PV work, okay? So enthalpy is also a state function. This is the big one we're going to be using a lot. So enthalpy values for specific substances cannot be measured directly. Only enthalpy changes can be measured. And so we sort of set things to a standard. So for chemical, so changes can be determined for different processes. All right, so the enthalpy change then is going to be, the change in internal energy plus pressure, volume, work, right? And I'm not going to say a whole lot about this. If this, let's replace that WV, or that W. I'm not sure if I gave myself room here. This, right, we know that from the first law of thermodynamics is Q plus W, right, plus PV. You see how I just replaced that? Just replace that right there, okay? And we also are going to define PV as negative W. So where P delta V is equal to minus W, and so delta H is equal to Q plus W minus W. And for a constant, that is at constant, this is at constant pressure. At constant pressure, this is going to be true. And so substituting, I just substituted that in the previous slide. Then in that case, delta H is going to equal to the heat at constant pressure, okay? And that's a key result that we're gonna use. So let's now talk about the notation we're going to use. Chemists use thermochemical equation to represent the changes in both matter and energy, right? You've seen things like this before. Here's a balanced chemical reaction. And we're going to now say that the enthalpy of this reaction, the change in enthalpy of this reaction, is going to be minus 286 kilojoules. And that gives us some measure of, or some way of expressing how much energy we get from this. It's going to be negative because we're getting energy from it. It's exothermic. Okay, so here's some important conventions that we have to appreciate. That if the change in enthalpy, let's see, of this reaction is minus 286, then if we double everything, it's going to be 2 times that, right? You see how we doubled that? It's going to be 2 times that. That's doubled. And if we take half of that, it's going to be that times 1/2, right? So this is an important, because it's extensive, so we can do this, right? An important factor to appreciate. Also, the change in enthalpy of a reaction depends on the physical state. So we are going to always write the physical state in the system, right? Because water at a gas, look at this, if we're taking these two gases and taking 2 water as a gas, we can only get 246 or 242 kilojoules out of it. If we take it all the way to a liquid, we get minus 286. Okay? And the third thing we have to appreciate is that a negative delta H indicates an exothermic reaction, and a positive delta H indicates an endothermic reaction, right? So consequently, if we take hydrogen gas and oxygen and we combine it, then we're essentially going to be burning it, right? We're going to get liquid water out of it, and we're going to get that many kilojoules out of it. But if instead we take water, liquid water, and we hydrolyze it, electrolyze it, so that we can break it apart into hydrogen gas, it's going to cost us 286, right? And so it turns out if we turn these reactions backwards, then we just take the delta H and flip it in sign as well.